Hello, everyone. Welcome to our talk today. Today we have the pleasure to receive Dr. Keiller Nogueira from University of Stirling. Thank you, Keiller, again for being here with us. This talk is organized by our student chapter here in Federal University of Mato Grosso do Sul. Our speaker today, Keiller Nogueira, has got a PhD in computer science from Federal University of Minas Gerais in Brazil in 2019. Currently, he is a lecturer at the University of Stirling. His research expertise includes machine and deep learning applied for pattern recognition, mainly in remote sensing applications. He has worked with a variety of high-impact applications that we are going to see during his talk today. Thank you, Keiller, again, and now it's your time.
Okay, thank you, Marcato, for introducing me, and thank you actually for inviting me to give this lecture. And today we're going to talk about deep learning applied in environmental studies. And this is the outline of the presentation today. I'm going to introduce a little bit more just the motivation, and I'm going to briefly explain about semantic segmentation, as this is the core of the whole presentation. And then I'm going to talk about 4 different applications I've been working the last couple of years. And I will end the presentation talking a little bit about the future opportunities that I see in this field. So let's start here. So the Earth's surface is constantly being modified. So here we have an example of Dubai in 1984 and Dubai in 2012. We can see that there is a bunch of new artificial islands, and it's essential for us to monitor these changes so we can understand what's changing and how this changing is affecting the world, and also how it's affecting us. So it's essential to monitor these changes. And the big problem here is that it's costly and almost impractical to monitor these changes via on-the-ground observations, because the place where we want to monitor can be really far away. So it's complicated to send someone there daily or weekly or even monthly to monitor, to check the place. And it's also complicated because of economical and human resources. And to save us, we have aerial and remote sensing images. So we can use this type of images to understand what's going on the Earth's surface without the need to send someone there. And the information extracted from this kind of images can assist in the understanding of several different events. So here I included 3 examples. The first one is for urban planning. So for example, if we need to define the best place to build a hospital or fire police department, so we need to understand what's going on in the city. And also for fire and flooding relief, so we can decide the best strategies to handle this kind of situations. And of course, it's not so easy, and extract information of this kind of images usually requires thematic maps. And when I say thematic maps here, I mean maps highlighting the areas that we are interested in. And here I put 2 examples of thematic maps. The first one for agriculture, where the highlighted parts, the white parts, are coffee crops. And the second one for urban scenes, where we have like roads and trees and houses. And we have a problem that to create these thematic maps using manual efforts is really low and costly, because we have like huge images, and we would need to do this over and over again if you want to monitor some area over time. So it's really complicated. And for this, we have automatic maps, automatic methods. So when I say automatic methods here, and relate this to thematic maps, I'm talking about semantic segmentation. So we will use semantic segmentation to create the thematic map for us. And nowadays, what we've been using is deep learning, mainly because it can learn specific and adaptable features and classifiers based on the data. So this is a good advantage when compared to the previous methods, the traditional methods. And among all deep learning methods, the most common for semantic segmentation is convolutional neural networks, or convnets. So I'm going to introduce a little bit about how we use convnets for semantic segmentation. So semantic segmentation is the task of assigning a semantic category to each and every pixel in an image. So we have an input image here in this case, and we're going to process this image somehow. And we want the output to be another image with every and each pixel of this image assigned to a class. And we do this with convolution networks. We usually have the input image, we have layers that process this image and learn the features and generate feature maps for us. And usually these feature maps, they have a reduced size. So we keep doing this, reducing the size, and we reduce the size because of different reasons. I'm saying more about why we're reducing the size because further in the presentation, this will be important. But we have more layers that process the feature maps and output other feature maps. And we keep doing this until we reach a point in the network where we output the coarse classification. And when I say coarse classification, it's like the classification of the input data, but in a small image, in a small scale. And from this coarse classification, we upsample using more layers and generate the final output, which usually has the same dimension or the same size of the input image. And this is what we want to do. And all the methods related to semantic segmentation, they have this kind of this idea. So the most common methods that we have are the fully convolutional networks, which is the case I just presented. And we also have the segnets or UNets or the convnets, which are slightly different because they are based on the encoder-decoder concept. So in this case, we usually have several layers that process the input and generate the coarse classification. And then we have a second part, which is the decoder, which is the mirror part of the encoder, which will upsample the coarse classification and generate the final result, the final outcome. So all the segmentation methods, most of them at least, they are related to one of these two strategies here, to one of these two networks. So now we start going to talk about the applications and how we use this concept or this idea of deep learning for semantic segmentation in our problems. And the first one is for floating identification. And the objective here is to identify floating areas from satellite images took during or shortly after a flood event. So here we don't have a hydrological model, so we can study and infer the areas that would be flooded. But we have the satellite images and just want to understand the areas that were flooded recently. And this is the result of a test called multimedia satellite test. It's like a contest that we participated together with some researchers from Unicamp, and we were considered the winner of this task. So before I explain the idea here, I'll explain a little bit about receptive field because it's kind of the core of the hypothesis of this part. So I said previously that when we have an input, we process this input with several layers, but we reduce the size of the input, the size of the feature map, or in other words, the output of the layer is usually a reduced version of the input. And there are several reasons to do this. And one of them is to increase the receptive field. And the receptive field is the area in the input data that influences the output pixel. So here's an example. Let's suppose we have an input and we process this input with a 3x3 filter. We have an output, and then we process again with another 3x3 filter, another output. Now this pixel here and the last output, it's influenced by this area in the middle layer, which in turn is influenced by the whole area in the input data. So this whole area in the input data is actually what we call the receptive field. And this is important because the larger the receptive field, the more context we have to work and to generate the output, the pixel. So the problem here is that what if we can increase the receptive field without decreasing the outcome, the output of the layer? So that's the idea of the dilated convolutional layers. This type of layer allow the filters to have rows or gaps between the parameters, and this allows the network to expand the receptive field, but preserving the feature map and the number of trainable parameters. So we're not increasing the complexity of the network. So in other words, we have this input. We process this using a dilated, this is the dilated filter in green. It's a 3x3 filter, but with one dilation. And we process again. Now we are not reducing the input size, or we're not reducing the output size. We are preserving the input size. But this pixel now is influenced by this whole area, which in turn is influenced by the whole input image. So now we can increase the receptive field or increase the area in the input data that influences the pixel, the output pixel. So based on this concept, on this idea of preserving the receptive or increasing the receptive field, preserving the feature map, here's an example. Forgot about this. This is an example showing how the dilated and the receptive field influences the outcome. So we have both paths here have the same receptive field, the green and the blue one. The green one, the red one, sorry, the red one is using standard convolution, the convolution that we usually use in convnets, and the blue one is using dilated convolution. But in order to have the same receptive field, in the red one, we need to downsample the input image, process with the convolution, and then upsample. And in the blue one, we don't need to do this. We just need to dilate the filter. So when we compare the final outcome of both ways, you can see that it's really different. And the one with dilated convolution, has more details. So that's one advantage of the dilated convolution. And with this in mind, we decided to evaluate in this contest how we would be able to learn, if we would be able to learn the segmentation without decreasing the input size throughout the network. So here's just a representation of the idea. We have the input size, we have a bunch of layers, but we're never reducing the input size, never. And we evaluated a bunch of different architectures, all of them based on dilated convolutions. So we evaluate networks varying from 4 to 10 dilated convolutions. And this is the outcome. We outperform all the baselines, the blue bars. And we can see that we have here very up-to-date baselines like generative diversion networks and VGG13, the convnet. So this is the idea I presented that I said there was an encoder-decoder architecture. So we outperform all of them. And this is some visual outcomes that we obtained. So the outcome of these paved the way of the next application I'm going to present. So with this first application, in this first part, we noticed that it was pretty good to preserve the input size. So we decided to keep looking, keep researching about this. And as I said, this paved the path for the second application, which is to distinguish coffee crops from non-coffee crop areas. And when I say here non-coffee crop, I say everything. There's not coffee crops like cities and roads and trees and forests and lakes and everything. Um, so for the previous application, we were working with small images like 256 by 256. And in this case here, we were working with huge images. So we're not able to process this huge image at once because of we didn't have computation capabilities to do this. We actually don't have nowadays. And so to process these huge images, we would need to split the input data into smaller patches and then process these patches. And this is kind of the standard of the literature nowadays, and or at least it was. And we have here the first one is we have input image. We split this input image in context windows, and then we classify. In this first case, the classification is a single classification, just saying if that context window is a coffee or non-coffee. In the second case, we have the input image, the original image. We create patches. I have a fully convolutional network, and we have a dense classification, and then the final map. In both cases here, we need to define the context window size or the patch size. And this is complicated. Uh, the literature usually does this in two ways. The first one based on the network or the architecture, actually. So if I have an architecture and I don't want to change anything, so I will create the patches that will fit to that architecture. So if I have an architecture that receives 100 by 100 pixels as input, I will create patches of 100 by 100 pixels. And the second case would be experimentally, we would evaluate several patch sizes and define the best one. But problem is that a unique patch size maybe it's not enough for understanding the scene. So here's an example. On the top example, we can see the smaller patch. It's hard to distinguish what it is. It's hard to say if it's a road or it's a roof. And as we increase the patch size, we can see that that is a car, and then we can infer that there is a road. And in the bottom example, it's very similar. When we see the small patch, we see that it's a car, and as we increase the patch size, we see an object, a white object, and the network might think that this is a car because it's very close to a car, and it's in the same direction, and it's kind of the same shape, but this is not a car. This is a container. It's different. So a unique patch may not be enough, and so the network starts working multi-context or multi-scale strategies. And the literature usually does this in two ways. The first one would be to extract features from multiple layers, concatenate these features, and process them. And the second one would be to combine the outcome of several networks. In both cases here, we are increasing the number of parameters, and we are turning the networks harder to train and more prone to overfitting. So what we propose here is a method that would aggregate context information without increasing the number of parameters and without increasing the complexity of the network. So what we have a patch distribution. It can be any distribution, uniform distribution or multivariate distribution, doesn't matter, unique model. And the distribution will be over all the patches sizes that we want to evaluate, and we have the training images. And the first step during the training would be to select a patch size based on the distribution. Then we generate a batch based on the patch size, on this patch size. And then we use this batch to train a network. In this case, it's a dilated convolution network, or again, a network that never downsample the input data, or never reduce the dimension of the input data. In this case, I need to mention here that we could use other networks here, like the SegNet or any encoder, decoder, or fully convolution network, but this kind of networks, they have some constraints here, because when we are using dilated convnets, we never reduce the input, so we can have input of any size. When we are using, for example, encoder decoder architecture that I previously explained, we reduce the size of the patch of the input, and if you give a small input, maybe we are going to reduce too much, and we're not going to be able to generate an outcome. So that's why it's complicated to use this training strategy with other networks. When we train this dilated convnet with this batch, the network will generate an outcome like the loss or the accuracy, and we're going to use this as an index to update the score or the distribution of the patches. And then we select again a new patch size, and we keep doing this over and over again, updating the distribution and getting a new patch size until we converge the network or we reach a certain number of iterations. And during the inference or during the testing, we just select, based on the distribution, the best patch size, and we generate the batch based, or the patches, all the patches in this case, based on this patch size. We use the pre-trained dilated convnet to segment all the patches, and then we recreate the final map. So with this strategy, we can aggregate multi-constant information without increasing the number of parameters and the complexity of the network, and at the same time, you can select the best patch size for the inference phase. We compared this strategy with several other baselines, the blue bars. It's worth mentioning that these baselines were all trained with the traditional training strategy commonly employed in deep learning, and we outperform all of them in terms of kappa. And more than that, it's worth mentioning that we outperform them having fewer parameters, sorry. So here I just included a graph to show that we are using fewer parameters. This is not for the coffee exactly. This is another dataset for the variant. I use this one to create this graph just because it's a more used dataset. So it's more common in the literature. And so I could compare the proposed method with several ones from the literature. And we can see that here that this graph is the overall accuracy by the parameters in log base. And we want here methods to be on the top left, so more accuracy, less parameters, fewer parameters. And we can see that we are almost there. We have very good accuracy, close to 90%, but fewer parameters. Worth mentioning that, again, the x-axis is in log. So one point here is equivalent to like millions of parameters. And here's the visual outcome of the method. So the right column, the rate 8 pooling, is the outcome of the network trained with this training strategy. All the others are the baselines, and you can see that we have less noise problems, and the roads are very defined. So The result was really good. And this one is this is another application for erosion identification, different from the previous one. Previous ones, this one is less focused on the methodology and more focused on the application itself. And the objective here is to identify erosion in under construction railway lines. And when I talk railway lines, I'm talking specifically about the Transnordestina Railway. And this is the outcome of a project in partnership with the Tribunal de Contas da União. So the problem is that they need to monitor the public constructions, and it's really hard to do this with on-the-ground observation because you need to send someone there. So here's an example. The figure is the Transnordestina, and you can see that it's really big, and it's hard to send someone there to monitor this on the ground. So they wanted to do this using satellite images, but even with satellite images, it's pretty complicated because like this is really huge. Here's an example of one image, and the railway was composed with I think 45 images like this. So it's a really huge data set. And they wanted to do this automatically to identify the erosions automatically. And you can see highlighted a small part of the railway and the erosions. And what we did here, we proposed a very simple method. We have all the image, the whole data set, and the railway shape. We would walk on this railway shape, creating crops around the railway. Okay, so we are actually discarding everything that is too far from the railway. We use a neural network to segment these patches. We recreate the whole image, and then based on this, we do some post-processing, but based on this, we create the final shape file for the TCU so they can use this and check for the erosions. And the outcome is really interesting here. What's really interesting here is that this whole pipeline was created and encapsulated as an ArcGIS plugin, which is publicly available for anyone. So anyone can download this and use. And we can use any network, any segmentation network in this pipeline. So we evaluated several networks, and we can see here that the dynamic convenet, which is the one I just presented to you, the one with the dynamic multi-context information, outperform all the other networks. And you can see this and the same outcome when we compare the visual results. You can see that the proposed method, our method, can learn the patterns and can better distinguish the erosions. And it's really hard. It's worth mentioning that this is a really hard task because it's hard to distinguish erosion from bare soil. And it's also hard to distinguish erosion because there are several different patterns for erosion. So it can be just a small erosion, it can be a huge erosion. So it's very difficult, very complicated task. And this is the last application I'm going to talk here. It's more related to phenological studies. And the objective here is to segment plants over time. And this is really important because we want to understand the life cycle of the plants and their relation with the climate conditions so we can understand what's happening. And I give you an example why this is so important. For example, if a plant is changing its life cycle, we'll understand that the plant is changing the life cycle, and we'll be able to go there and pollinate this plant. So it's really complicated, and this is kind of a first step towards a large objective, which is to fully understand what's going on and how the plant is uh, acting and reacting with the climate changing and everything. So here's some examples of the images I've worked in this application. These images are from drone. The bottom line, they're all from drone. They're not satellite images. And the problem here is that it's really difficult to capture these images. So there's a lot of missing data. Here we are working, as I said, we want to segment plants over time. So we are working with time series data. And so because it's really difficult to segment the plants, to collect the plants, to collect the images, then it's hard to have a good time series. So there's a lot of missing data in these data sets. So we can have a whole time series, but there's a lot of missing data. So we propose a method to handle this somehow. And the idea is that we would have a bunch of patches. Each patch here would be a timestamp. We would have specific layers for each timestamp. And so we have one specific layer for connected, or it could be layers actually, connected to a timestamp, another one to another timestamp, and so on. Then we would combine all these timestamps together and generate the final output. Interesting things here. By doing this way, if we have a missing data, we can just drop the branch related to that timestamp. So we have, as I said, we have specific layers related to each timestamp. So if that timestamp is missing, we can just drop the branch, and the network will automatically reweight the weight or the parameters over the other layers, the other specific layers. And also we evaluate different networks here, including the one I mentioned in this presentation with dilated convolution. So we also evaluated here a fully dilated convolutional layer, convolution network. Okay, and we outperform the baselines in blue. And as I said, this is a first step towards a huge objective. And there are several partners, biologists, actually using this method for the understanding of the life cycle of the plants. It's everything we wanted, right? So this is all the applications I've been working in the last couple of years. Everything I've talked to here, all the codes, they're all available. You can access all the codes. The ArcGIS plugin is also available. And so in the end, I'll give all the details to access. And everything I've mentioned here is published recently. So you can also, if you have any doubts, you can contact me and I can give you directions or the paper so you can take a look. If you have any questions, feel free to ask me. And now I'm going to talk more about the future opportunities, or what I see that are the future opportunities in this field of deep learning related to environmental studies and segmentation. So all the applications I've talked in this lecture, they all use only images, satellite images or drone images. But what if we use more than images? So I think in the future, in the near future, actually, we're going to use the idea of Internet of Things, or the idea of having multiple sensors, and we're going to combine these satellite images, drone images, sensor data, videos, and everything else. We're going to combine everything to produce better methods and generate better outcomes. and these outcomes can be like flooding areas or water pollution, so we can understand how the fishes are handling, coping with this, and you can also combine this information to understand the air pollution or the air humidity, so we can understand how the birds are coping with this. So I think one future direction would be to sorry would be to combine this kind of features, multiple features coming from multiple sources. Another one would be to better exploit the patterns from other scenarios. So here I'm talking using deep learning with less data. And this is kind of related to meta learning and domain adaptation. So for example, let's suppose I have annotated training sets for coffee trees and for orange trees. And now I want to segment trees, regular trees, but I don't have ground truths for the trees I want to annotate. I want to segment. So what I want here is a machine learning model that would learn from the coffee trees and from the orange trees and would apply this knowledge to the trees, to the regular trees. Because, I mean, there are trees, right? They're all trees. So they would need to connect the training set and the test set. They would need to connect to each other. So during the training procedure, so the model can learn what patterns it should focus on, so it can improve the performance and generate a good outcome. So that's one trend I think that we're going to see in the future. Models that would use annotated data sets to classify new data sets. So I think this is kind of a new trend here. And the last one, it's the segmentation using fewer pixels. So here I'm talking about sparse labeling and interactive segmentation. So usually nowadays, when we talk about segmentation, we are usually using as ground truth the dense map of all the pixels in the image classified. But I think in the future, we need to create methods that would be able to do this segmentation without requiring all the pixels to be annotated, to be classified. And here's an example. So instead of having all the pixels, you can just have like 3 or 4 pixels, and you can use the knowledge captured or learned from these pixels to annotate all the other ones. So I think this is also a trend for the future. And I think this is kind of, there are several works coming out right now with interactive segmentation, but I think there's a lot of things to do here. Actually, I think there's a lot of things to do in all these 3 topics that I talked to, 3 future opportunities that I talked. I think there's a lot of things to do, and so I think it's really interesting. And so that's my presentation. Again, there's my mail here. You can email me if you have any further questions after we finish here. And all the codes, all the applications I presented here, as I said, the code are publicly available and they're all in my GitHub. It's the last link in this slide. So you can access and download the code, and you can run your own data set. And there's other links where you can find my research, and you can contact me, and you can talk to me. Okay, so thank you.
Thank you, Keiller. Thank you very much for your presentation. Very, very interesting. So we are open for questions here. So please, you can comment, and we are going to. But now I will ask you some questions. Very, very interesting your presentation. The first thing is about your codes and also the data set. This is very important for our community to make it available, because it's very important. And this is, I would like to talk about this, which contributes to the community, which is very important for deep learning community. Thank you very much for this.
Yeah, so I think it's essential for us to always provide codes and data sets available, so we can allow the reproducibility of our work, and also you can encourage other works to improve our own work and improve the community as a whole. So I think it's essential to always uh, put codes and data sets available. All my codes are available on GitHub, and the data sets I use uh, always, every time I can, I put them available. I think I put 2 or 3 data sets available recently, so every time I can, I'm always putting data sets available together with my work.
Congrats, thank you, and thank you. The community thanks you for this. It's very important. All the reviewers, when we give some review to a journal, all the reviewers see this with good eyes, because it's very important for us, for the community. Thank you.
Yeah. Thank you.
Nayara, other questions?
Let me see. We have no questions on the
Oh,
chat.
I have some. So, you talk about multi-source, the combination of multi-source data set. I truly believe that this is the future, because uh, one data set is better for one thing. And for example, if we have UAV data set, it's better to see some detailed information. But it's very difficult to take image from large areas, and optical satellite images it's better. So the combination, not only in this case, I believe that's very important. So, for example, it's very common applying some super resolution in deep learning. What do you think about this technique? About I don't know if it's a possibility of combining multi-source, applying some of these techniques. What do you think about?
Yeah, it's possible to apply to apply multi-resolution, or there's methods of high resolution to kind of create a standard, a default, so you can process all the data all together. And actually, I think there are some works doing this, but this is something that needs more exploration. It's something that's beginning. It's in the beginning right now, so I think more and more we're going to see works trying to combine all this, everything, to put everything together, so they can reuse or combine information from multi-source, and to reuse information from source, annotated information from sources that they already have. And because I mean, deep learning requires a lot of data. This is a thing, a fact. And now we need to. This is kind of the biggest challenge of deep learning. And now, one thing is to face this challenge and to find ways to overcome these. And one way would be to try to use the data from other sources, and because we don't have, then we would not need to annotate new data sets. So I think it's a future trend.
Yes.
But again, I think there's a lot of things that we need to research.
Yes. So, in my opinion, the limitation of using deep learning in remote sensing is regarding the what you said about each pixel has to be a label, and it's not easy take an imagery from a large area, and also each pixel we have to draw it. So it's very hard. You showed the example with a bicycle, but for remote sensing, I believe it's more difficult to
Yeah,
do
it is more
this. So
difficult because with remote sensing, we usually don't have a clear definition of foreground and background. So here, for example, in this image, in this example, we can clearly see that the foreground is the kid and his bike, and in the background is the sand and the path. So in remote sensing, we don't have this. All pixels need to be handled uh, in the same way. So it's way more difficult, but I think this is something that we need to face, we need to overcome. We need to create ways of using less pixels to annotate things because, I mean, annotate things, create data set is a complicated task. It's really
yes,
boring and it's creating ways of to simplify this process would be the best thing.
yes, yes, yes. In this topic, what do you think? What are you as an expert in deep learning about unsupervised techniques? Uh, because most of the models today requires a lot of data, training data set. So, uh, did you see an uh, advance in this thematic
Unsupervised, you mean uh, in
without
general, or
your
we focus on semantic segmentation?
oh, in general, I don't know what do you.
Yes, there are some works coming out for unsupervised learning, but this is it's not as much explored as supervised, of course, but there is some good works coming out, not exactly for remote sensing, but I'm talking more in general. And I think uh, it's a trend as well, but it's difficult because uh, I mean, unsupervised compared to supervised, it's there is a gap. There's still a gap between unsupervised and supervised methods, and so if you want to choose something for you're creating a product and you want to choose something, you'll probably go with supervised because there is a gap there. And so until this gap is filled, I think everyone will still supervised methods will be more explored than unsupervised. But I think eventually this will change and there more supervised methods will come and this gap will close everything. I think everything we're going to choose between supervised and unsupervised. I think in the future we might see something like this.
Yes.
And choosing between supervised and supervised will not make a lot of difference anymore.
Uh, I hope yes, it's better. But yes, very very interesting your talk. And other other thing that I believe that it's very important because you concluded your PhD in 2019, and now you are in the University of Stirling. You are a Brazilian guy, a researcher that's there. So most of the public that is watching you here is from our master and also PhD students. So I don't know. Please tell us something about this experience. I already talked to you about this, and it's very interesting. And also to motivate our students to be outside. We in general we have many opportunities here in Brazil. Not exactly now, but the near future we have too many opportunities to go outside Brazil to make some PhD part of the PhD course,
Yeah.
and some students believe. what do you think about this? Because during your PhD, you went outside, and
I did.
please tell us.
I did part of my PhD in France, in Grenoble, and it was really great because I got to know other people, and I got to research with other people, and to see uh, new ideas, and it was really interesting to learn from these people. It's a different way of thinking, and it was kind of essential to for me. I mean, to as a professional as well as a person, to learn from these people. It was really great for me. And but I spent 1 year there, almost 1 year actually, and then I went back to Brazil. I finished my PhD and came here. Uh, it's a little different because here now I'm more working with lectures and stuff. I'm not only researching. Uh, but the experience is great, the same, because I can get to know different ways of thinking. Uh, I mean, everything is different from the way the, the teaching is, from the projects you submit, from the research. Everything is different, and it's really nice to understand this, to see, and to to uh, be able to be part of it. It's really interesting.
Yes, very nice.
Keiller, we have a question here.
Yep.
Mateus Barros is question. Keiller is indeed a great example of a successful researcher.
It's
Oh, it's not a question. Sorry, it's
Just a comment.
Yes, just a
Yeah.
comment.
Thank you, Mateus.
Mateus is also a
Yeah.
colleague
Yeah, he's
from the same university that you concluded your PhD. Yes.
yeah. We work together. We are from the same lab and the same research group, so we work together. And uh, he is working with, or at least he was, but working with uh, resolution, super resolution. So uh, yeah. So thank you, Matheus, again.
That's great. I have other questions here, but after we can talk about this. So I don't know. We have more 5 minutes.
Yeah, you can if you want to ask your questions, go ahead.
Yes, even in Portuguese, no problem.
Yeah,
Portuguese.
it can be Portuguese or in English. No, Marcato, if you want to ask your questions as well, feel free
Yes.
to ask. If
Uh,
Nayara wants to ask anything, I mean, she's going to work with semantic segmentation, so I think she's kind of one of the most interested in the presentation.
yes. Uh, I have some question about instance segmentation. I don't know if it is
Yeah.
possible to make some comments about it.
So instance segmentation, it's a combination of object detection and semantic segmentation. So in object detection, usually we detect the object. So if you have multiple objects in the scene, like for example, if you have multiple persons in the scene, we detect multiple persons. And in this case, we kind of, each person will be kind of a unique bounding box. Okay, so bounding box because I'm talking about object detection.
Okay.
And in the instance segmentation, we are going to combine this idea of object detection with semantic segmentation. So after we detect the bounding blocks of a person, we are going to segment the area inside the bounding box, and then we are going to locate and segment the person. So each person will be segmented, will be located in the bounding box and segmented with a mask. And I think there's a lot of methods coming out of instance segmentation, like the mask RCNN. We use the mask RCNN here. We compare the mask RCNN, which is an instance segmentation method. And there's other methods for instance segmentation. And it's a really interesting method. It's, as I said, slightly different from segmentation, but can be used for segmentation. And I think, but the same problems apply here. You require a large amount of data, and so I think even for when we're talking for instance segmentation, the future opportunities that are talked about apply, and I think we can. If you want to use instance segmentation for something, we would need a large amount of data, so we would need the future. I think we will need methods that would be able to do this process with less data or with fewer pixels or with combining information from multiple sources. And I think this is kind of the future right now, even for instance segmentation.
Okay. Keiller, now I have a question. Pedro Zamboni is asking, could you talk about how to deal with imbalanced class in remote sensing?
So this is a complicated thing to handle. I had a lot of problems with this, and there is a bunch of strategies that you can try. I mean, from the basics, one is to balance your data set based on the class that has fewer samples, or you can try to balance based on the batch, or you can try to balance based on the final outcome. So you kind of give weight for the class that has more weight for the class that has fewer samples and less weight for classes that have more samples. So there are several ways of handling this, but this is a complicated thing. And for me personally, I think I tried all. I gave you 3 ideas. Okay, balance before start the training, balance based on the class with fewer samples, balance in the batch. So the batch would always have the exactly same number of classes, or to balance in the final outcome, weighting the loss. For me personally, I think the first one is the one that worked better. I usually, if I have some problems with imbalance, I usually try to normalize based on the classes or the class that has fewer samples.
Um, a colleague is have some Ana Paula is having some difficulties in including her question in YouTube. Nayara, please check there. She said that she sent a question, but is not here for us. But mainly the question, Keiller, that Ana Paula said, is about the linear feature, as you showed to us, about road mapping, which is a linear object. So she is asking about if you have some experience in mapping other linear objects or something like this. For example, you use your method to map the roadway, the roads, okay?
Yeah.
So is it possible to use, for example, semantic segmentation methods to map linear features, not features, sorry, some linear objects such as roads, plantation, rows, or something like this. Did you assess your method to this task of linear mapping?
No, I've never, but I'm currently working in a project to map roads in Brazil. And when I say roads, I mean all types of roads. Can be a railway or can be a small road. And I'm currently working on this project, and it's kind of complicated because because of the patterns of different roads. So we are working using the using the north of the Brazil, more or less, and it's really complicated. But there are some works related to this. Okay, I've been reading a little bit about this, and there are some works related to I mean to linear objects like roads, and we are starting this project right now. We are currently evaluating the existing architectures, including the ones I mentioned in this presentation, but I've never evaluated these methods I proposed and this kind of application. Aside from the railway identification, the railway actually erosion identification that I work with the railway. Aside from this one, I've never applied the methods on other linear objects, on the detection of other linear objects. And I'm currently doing this right now. And as soon as I have some outcomes, I'll keep you posted. I'll post something and to let you know. But I think again there are some really interesting works. If she is interested in working with this, there are some really interesting works, and I can share the works that I've been reading with her if she wants to.
That's great, Keiller. One thing about deep learning it is because when we train the model, it requires a lot of time, not only time but also good GPUs and which is very important. But after the training, we have the inference time it's very interesting, and we have some fast solutions. So after training the model, and for example, in applications of mapping roads, can be very interesting to use deep learning because we can make some maps from large areas,
Yeah,
and we have some values because we have the roads here in Brazil, some shapefile from roads that are not accurate enough, but can be some initial values to perform after the mapping.
yeah. So that's the main idea. It's totally true what you said, and that's the main idea what we want to do right now. We want to use part of Brazil, of the roads in Brazil, to train a model, and then the train will take a while, probably hours, maybe days. I mean, I've trained models that took like weeks, so maybe it'll take some days to train. And but after that, we can apply this trained model to to other states of Brazil. It will not take so much time. Of course, it will take a while because we're talking about Brazil, which is kind of the one of the biggest countries in the world. But it's proportionally speaking, it's way less time than the time uh, spent to train the model.
Yeah, that's right, Keeler. I believe that it was very interesting, Keeler. Thank you very much for being here with us and to give us this excellent talk. Thank you very much. And
Thank you
Keeler,
for inviting me.
we also have Keiller. This video will be online, so you can take his email and also send some email. Keiller is very gentle person, a very nice person, and also answer our emails. And
It may take a little while, but I will answer.
Yes.
I swear I will answer. I can see Ana Paula asked something here. Yeah, I can see. She asked about if I try to apply standard machine learning like random forest. No, in this case, I did not try to apply standard machine learning approaches because this, as I said, this project was in partnership with the Tribunal de Contas da União, and they wanted deep learning. They said this to us: we want deep learning, we want deep learning, we want deep learning. So we only apply deep learning in this case, but I think it would be totally fine to apply other methods, other standard machine learning methods. There are some methods, new methods not related to deep learning, like XG boosting or something like this, that that is really interesting and we might use. So I don't think deep learning is the solution for everything, but they really want deep learning, so that's why we only apply deep learning in this case.
That's right.
Keiller, on behalf of our MES GRSS chapter and our UFMS branch, student branch, we thank you for this opportunity. It was a pleasure to have you here. And by now we are finishing this live. But if someone have a question, you can comment after Keiller could have some answer someone, or contact Keiller for more information. Thank you so much.
Thank you for inviting me, for having me, talking a lot here, and I hope to give maybe another lecture next year or next time.
Yeah.
Yes.
Thank you, Keiller.
Okay.
Thank you very much.
Bye-bye.
Bye-bye.
Bye.